Imagine navigation systems that don't rely on Earth at all. Spacecraft parts that can literally print themselves stronger than ever.
Yeah.
And humanity's presence out there, sustained by its own orbital internet.
Mm-hmm.
Well, this isn't science fiction anymore. It's the reality being built week by week. Welcome to Tomorrow Unveiled, your guide to the innovations shaping our world.
Glad to be here.
This week on Tomorrow Unveiled, we're taking an extraordinary journey. It's all about beyond Earth, this week in space.
It's been a busy week.
It really has.
Yeah.
Our dedicated research team pulled together an incredible stack of sources, and they reveal this really pivotal moment in space tech advancement.
Definitely.
Looking at this past week, say August 15th to 22nd, 2025, it seems less about single big discoveries and more about the tangible steps, building resilient, sophisticated off-world infrastructure.
Right, the building blocks. It's about the how we're going to do things out there, not just the what's.
Exactly. So our mission today is to dig into the most important cross-corroborated developments, the things pushing humanity literally beyond Earth.
Mm-hmm.
We're talking revolutionary navigation, space-grade superalloys hitting the market, the first steps towards an orbital economy.
That's a lot to cover.
It is. So get ready for some aha moments.
Mm-hmm.
We want you to feel truly clued in about our future among the stars. Let's jump right in.
Okay.
All right, first up, our research team flagged this as really significant. The launch of the U.S. Space Force's X-37B Orbital Test Vehicle, OTV-8, that was August 21st.
Right, the uncrewed space plane. It's basically a flying lab for testing new tech.
And the tech it's testing could fundamentally change navigation and communication in space, couldn't it?
That's the key takeaway, yeah. What's really striking is the dual payload. It's carrying a quantum inertial sensor and high-bandwidth laser communications.
Okay, let's unpack that. Why is that combo so important?
Well, from a strategic view, it's all about resilience, making sure critical assets can operate on their own without relying on traditional GPS.
Especially where GPS might be jammed or just unavailable.
Precisely. In contested environments, or even just deep space exploration later on.
A quantum inertial sensor. Sounds very sci-fi.
Yeah.
What makes it so revolutionary for navigation?
Well, the sources describe it as the highest performing quantum inertial sensor ever used in space. It's different from older gyroscopes.
So...
It uses something called atom interferometry, basically leveraging the wave-like properties of atoms to measure acceleration and rotation with incredible precision.
Wow.
But the real game changer, its accuracy doesn't degrade over time. It doesn't drift.
It just stays accurate forever.
Essentially, yes.
Yeah.
Which makes it vital for those GPS-denied situations we mentioned, both military and, future deep space missions where there's no GPS anyway.
Yeah.
It's like an unjammable, perfectly consistent compass.
Okay, so a spacecraft with this could navigate perfectly anywhere without an external signal. That's a huge shift.
It really is.
And the other payload,
Yeah.
laser communications.
Right. OTV-8 is also testing high-bandwidth intersatellite laser comms.
Faster data.
Much faster.
Yeah.
We're talking data rates potentially 10 to 100 times higher than typical RF systems. So moving massive amounts of information really quickly.
Okay.
And crucially, lasers use a very narrow beam. That makes the link inherently more secure, harder to jam, harder to intercept.
And I think our research mentioned this wasn't just for military links, something about commercial networks.
That's a really important point, yes. A key goal is testing links with commercial satellite networks.
Why is that significant?
It signals a strategic shift, moving towards a kind of hybrid military-commercial comms architecture.
Using the commercial constellations that are already going up.
Exactly. Leveraging that boom to enhance robustness, enhance scale, it makes the whole network much more resilient and interconnected.
So the big picture here. These tests are laying the groundwork for spacecraft that can operate stealthily, navigate perfectly, and communicate securely and incredibly fast.
It potentially shifts the strategic balance in orbit, and it paves the way for that super secure, lightning-fast internet, maybe even across the solar system eventually.
Okay, wow. Now, let's switch gears a bit. Materials science. This is really interesting. Our sources detail a breakthrough from NASA, a new 3D printable superalloy called GRX-810. Sounds like it could completely reshape how we build high-performance parts.
It definitely raises that question. How do we make materials tough enough for rocket engines, for the harshness of space, but also make them efficiently? GRX-810 seems like a really compelling answer.
And it was designed specifically for 3D printing.
From the ground up, yeah. for additive manufacturing. It's not just an improvement. The research suggests it's a generational leap in
A
performance.
generational leap. That's a strong statement.
Yeah.
What makes it so special? How does it work?
Okay, so it's what's called an oxide dispersion strengthened alloy, an ODS alloy, mostly nickel, cobalt, chromium. The revolutionary part is these nanoscale yttrium oxide particles spread uniformly throughout the structure. Think of them like microscopic rebar, making it incredibly tough.
Tiny reinforcing bars. Okay.
And because it's optimized for 3D printing, specifically laser powder bed fusion, you can create parts with incredibly complex internal shapes.
Like cooling channels inside a rocket nozzle, things you couldn't make easily before.
Exactly. Impossible to make with traditional forging or casting. So you get better performance and this incredible toughness.
How tough are we talking? The numbers sounded pretty wild.
They really are. The data shows it can survive over 1,000 times longer than the alloys currently used under really high stress and high temperatures over 2,000 degrees Fahrenheit. That's around 1,100 Celsius.
1,000 times longer.
Yeah. And even more impressive, some initial large-scale production runs actually lasted twice as long as even NASA's own small batch samples predicted.
Wow. So it's not just strong, it's incredibly durable. That's huge for reusability, isn't it?
Absolutely. It profoundly impacts mission longevity and the economics of reusable rockets.
And this isn't just stuck in a lab, right? The sources mentioned commercialization.
Correct. It's moving out. NASA awarded co-exclusive licenses to 4 American companies to actually produce and market GRX-810.
So it's becoming a commercially available product.
Which is huge. It, democratizes access to this critical enabling tech. It lowers the barrier for innovative startups, smaller companies, anyone developing new rocket engines or spacecraft.
So the real aha here isn't just the material itself, but that making it available commercially could just unleash a wave of innovation.
Precisely. It shatters a cost barrier, potentially redefining who gets to build the next generation of spacecraft. Imagine 3D printing a rocket part that lasts 1,000 times longer.
Okay, incredible stuff. But space isn't just about getting there or building the parts. It's what we do when we're there.
Right, the applications.
And our sources point to the upcoming SpaceX CRS-33 mission to the ISS, launching around August 24th. It looks like a real proving ground for a sustainable orbital economy.
It really does. And what's fascinating is how the different payloads connect. You've got an orbital data center, biomanufacturing experiments, even a new station-keeping capability for the Dragon capsule itself.
They seem kind of disparate at first glance.
Yeah, but if you look closer, they're deeply interconnected. This whole mission, it feels like it's about building that foundational digital and logistical backbone for humans living and working in space long term.
Making the station more autonomous, more capable. Let's start with that orbital data center. What is it?
Okay, so the flagship payload is the Axiom Space Data Center Unit 1. It's a prototype powered by Red Hat Device Edge.
And the goal?
It's the first test of running, essentially, terrestrial-grade edge computing hardware and open-source software in space in that challenging environment.
Why do that? Why put a data center up there?
The main objective is real-time data processing in orbit. Right now, a lot of data has to be sent back down to Earth for analysis because bandwidth is limited. This allows for faster decision-making, more autonomy for experiments, for manufacturing, basically bringing the cloud, or at least the edge of it, to space, bringing compute power to where the action is.
Enabling faster, more independent operations. Makes sense. And you mentioned manufacturing. Biomanufacturing.
Yes, CRS-33 is carrying a whole suite of biomedical experiments.
Like what?
Things like materials for 3D printing medical implants. These ones are designed for nerve damage repair. There's bioprinted liver tissue to study how blood vessels develop in microgravity, and bone-forming stem cells, researching ways to stop astronauts losing bone density.
So really focused on enabling long-duration human missions, keeping people healthy out there.
That's a big part of it, yes, achieving medical autonomy for trips to the moon or Mars. But it's also about using microgravity to make unique biological products, maybe better protein crystals for drugs that could benefit us back on Earth.
That sounds incredibly ambitious. And how does that orbital data center tie into this? You said they were linked?
Absolutely crucial link. Think about it. Future bioprinters, advanced manufacturing in space. They'll generate tons of data.
Right.
Having that data center right there allows for real-time analysis, maybe AI-driven quality control, autonomous adjustment. It's essential for doing precision manufacturing reliably in space.
Okay, the computer enables the factory. Got it. And there was one more piece, something about the Dragon spacecraft itself.
Yeah, this is a really interesting development. The Dragon on this mission has a boost trunk,
A boost truck.
essentially an independent propulsion system attached. It allows the Dragon spacecraft to use its own Draco engines to perform reboost maneuvers for the ISS, to push the station higher.
But don't Progress or Cygnus vehicles usually do that? Government vehicles.
Historically, yes. This will be the first time a commercial cargo vehicle provides that station-keeping capability.
So SpaceX isn't just delivering cargo anymore.
Exactly. It shows this evolution. Commercial logistics providers aren't just space trucking anymore. They're becoming integral partners in actually sustaining and enhancing critical space infrastructure. Maybe even satellite life extension or debris removal down the line.
So the real insight, the aha moment here, is seeing how in-space computing could transform future stations from just labs into these self-sufficient, intelligent hubs.
Yeah, enabling real-time manufacturing, medical breakthroughs, right there on site, without constantly needing Earth.
Like you said, a self-sustaining factory and hospital powered by its own orbital internet. That's the future these missions are actively building.
That's the vision, yeah.
Okay, let's shift gears slightly again. Blue Origin. Our research team noted their uncrewed New Shepard flight, NS-35, targeted for August 23rd.
Right, the suborbital rocket.
Now, this might sound less, glamorous than an orbital mission, but the sources stress it's really important for long-term goals beyond Earth.
Absolutely. These suborbital flights are incredibly valuable as cost-effective microgravity labs. It really addresses the question, how do you test critical tech for the Moon and Mars without the huge expense and complexity of going all the way to orbit every time?
So NS-35 is a demonstration of that, a proving ground.
Exactly that. It offers a vital testbed.
What kind of things are they testing on this flight?
Two key payloads really stood out in the research. First, the EDR fuel cell, that's from Teledyne and NASA.
A fuel cell, like for power.
Yes, but this one generates both electricity and drinkable water from stored hydrogen and oxygen.
Power and water, essential.
Totally. It's a cornerstone technology for sustainable, closed-loop life support and power systems. Think future moon bases, Mars habitats, making them self-sufficient.
Definitely need that. What's the other key payload?
It's called MUD, microgravity ullage detection. That's from Carthage College and NASA.
MUD, what does it do?
It's testing a non-invasive way to measure how much propellant is left in fuel tanks in microgravity. It uses acoustic vibrations.
Measuring fuel level seems basic, but I guess it's tricky in zero-G.
It's notoriously difficult, actually. Liquids behave weirdly without gravity pulling them down, but reliable propellant gauging is absolutely critical. You have to solve it to enable in-space refueling.
Which you need for serious interplanetary travel, right?
Essential for anything complex in cislunar space or going further out. You can't plan deep space journeys if you don't know exactly how much fuel you have.
So how did these quick suborbital flights really help speed things up? They only get a few minutes of microgravity.
Those few minutes are high-quality microgravity, though. It's enough time for researchers and engineers to test hardware, check if their models work, gather crucial data.
And they can do it much faster and cheaper than an orbital launch.
Exactly. It's an iterative process. You can test, tweak, fly again relatively quickly. It significantly accelerates maturing these critical systems needed for the Moon, Mars, and beyond.
So the takeaway is these seemingly short flights are actually punching way above their weight.
You could say that. They're dramatically speeding up development of essential tech for living and working off-world. So yeah, just suborbital, but the implications are definitely deep space.
Okay. We've covered some amazing progress, truly groundbreaking stuff, but space is hard, right?
Always.
And our sources definitely highlighted some important challenges, some reality checks. It's not all smooth sailing.
No, and it's critical to ask as we push these boundaries, what are the practical hurdles? What do we need to overcome for this to be sustainable long-term? These challenges, regulatory, environmental, operational, they're all part of the picture.
What are some of the big ones, especially for that cutting-edge tech, like the orbital data centers?
Well, for in-space computing, the environment itself is brutal. You need extreme hardening against cosmic radiation. Managing heat without air is tough.
Right, no convection cooling.
Exactly. Power demands are huge, and reliability has to be near perfect because you can't just set a technician up to fix it easily.
And cybersecurity must be a nightmare for critical orbital infrastructure.
A massive challenge, yes. Protecting data and control systems in space is just as vital as on Earth, maybe even more so.
And it sounds like sometimes the tech is moving faster than the rules and logistics back here on Earth.
That's definitely a factor. Regulatory processes Like the sources mentioned FAA environmental reviews for new launch systems like Starship, they struggle to keep pace.
And supply chains?
Supply chain resilience is always a concern, especially for specialized components. It's prompting diversification, like, developing methane engines, partly to reduce reliance on specific international suppliers.
And we can't forget the people involved, the astronauts. What about the risks to them on long missions?
That's paramount. Astronaut health is critical. We're still learning how to best mitigate microgravity's effects on the body, brain, balance immune system, bone density.
And radiation exposure.
And cosmic radiation, yes. That's why missions like Russia's Bion No. 2 biosatellite, flying mice and other organisms, are so important. They gather vital data to help us protect future human explorers.
And as space gets busier, traffic jams.
That's becoming a really serious concern, the sheer number of satellites going up, especially these mega constellations.
Like Starlink, the sources mentioned SpaceX hit its 100th Falcon 9 launch just this year.
Right, launching over 1,700 Starlink satellites in 2025 alone. It leads to orbital congestion, collision risks. There's an urgent need for better space traffic management and ways to deal with debris. It's like building highways without traffic lights or tow trucks.
And finally, all this advanced tech, it has strategic, even military implications, doesn't it?
Undeniably. The X-37B we discussed, other nations' developments, it highlights the increasing militarization of space that brings concerns about dual-use tech, transparency, arms control, basically preventing conflict up there. Maintaining stability is crucial as space becomes even more vital.
So yeah, these challenges are real. They remind us progress in space is definitely a marathon, not a sprint.
Absolutely.
But despite all those hurdles, the overall picture from our research this week feels incredibly optimistic and ambitious.
I agree. These advancements aren't happening in isolation. They really are laying the cornerstones for an integrated, multi-world future. It feels like the timeline for humanity's expansion is accelerating.
So painting that picture, what does that near-term multi-world future look like based on the sources?
Well, very soon, within the next couple of years, we expect Artemis II to take astronauts around the moon that's planned for 2026.
The first crewed mission back to lunar space in decades.
Followed by Artemis III landing humans near the lunar South Pole in 2027. And that's not just flags and footprints. It's about establishing infrastructure. NASA's Gateway Station, commercial habitats, focusing on sustainability, using local resources, in situ resource utilization.
Living off the land, lunar style, and beyond the moon.
Mars is definitely in sight. Plans like Blue Origin's concept for a Mars telecommunications orbiter, maybe late 2020s. The ongoing Mars sample return missions around 2027, 2028, and even planetary defense is growing, like JXA joining the mission to study the asteroid Apophis. It shows our reach expanding into deep space.
So, moon first, then Mars, while keeping an eye on the neighborhood. What about the commercial side back in Earth orbit?
That's booming too. The ISS is set to retire around 2030, which is driving the development of private space stations, Axiom Space, Orbital Reef, others, new destinations for research, maybe tourism.
Right.
And if launch costs keep dropping, especially with Starship's potential, concepts like space-based solar power or large-scale manufacturing in orbit, using tech like GRX-810 3D printing, they start to look much more feasible. The commercial economy is really taking flight.
It feels like a global effort now, too, not just one or two countries.
Absolutely. It's increasingly international. Significant contributions from the U.S., Europe, Russia, China, India with their Gaganyaan crude program, and Surya heavy rocket concept, Japan, New Zealand.
Which creates both competition and collaboration.
Exactly. You see both. Like the NASA ISRO-NISAR satellite is a collaboration. It really underscores the need for international standards, clear frameworks to ensure we cooperate and avoid conflicts as we all move out there together.
Okay, before we wrap up, we genuinely love hearing your thoughts. If you're watching on YouTube or listening on your favorite podcast app, please drop a comment. Let us know what you think about this Beyond Earth This Week in Space deep dive.
Yeah, what breakthroughs stood out most to you? What are you most excited about?
And if you're finding this insightful, especially on YouTube, please take a second to like this video, subscribe to Tomorrow Unveiled, and definitely hit that notification bell so you don't miss future updates.
And for our audio listeners, if you're on Apple Podcasts, Spotify, somewhere like that, a rating and review for Tomorrow Unveiled would be amazing. It really helps new people find us.
It truly does. Okay, so wrapping up today on Tomorrow Unveiled, we've really journeyed through a packed week in space, haven't we?
Monumental progress, really.
We saw the X-37B pushing quantum navigation and laser comms. witnessed that game-changing GRX 810 superalloy Go commercial,
Explored the foundational orbital computing and biomanufacturing, heading to the ISS on CRS-33.
and highlighted those crucial suborbital tests from Blue Origin, accelerating deep space tech. All these pieces detailed by our research team. They really showed the building blocks of a beyond Earth civilization starting to click together.
It's an optimistic view, but realistic too, acknowledging those challenges.
Definitely. Celebrating the ingenuity, the collaboration, but keeping eyes open about the difficulties. So as we see all these nations, these private companies, laying down the tracks for moon bases, Mars networks, orbital factories, maybe the provocative thought to leave you with is this.
Okay.
While managing the challenges, the traffic, the strategic stability, fostering real international cooperation become the ultimate test. The test of whether humanity is actually ready for a truly multi-world future.
That's a deep question. What rules do we need when there are factories, data centers, even hospitals in orbit, and outposts on the Moon and Mars?
Something to think about. Thank you for joining us on Tomorrow Unveiled.
Thanks for listening.
Until next time, keep looking up and keep exploring the future.